Hello. In this video, I'm going to go over a Matlab program I designed that can simulate a bunch of different configurations of an airplane and ultimately scores them so you can evaluate which design for your plane might be best. So I'm going to start over by explaining how it loops through the various parameters, go through the single plane test, which calculates a bunch of different parameters. And as I do that, I'm going to explain each of the functions in turn and basically go through the math and show my source for each of that. And then I'll probably create another video that's just explaining the functions so you can skip through those faster. So in my loop through shape parameters.m file, I define a various range for the span of the wing, how long it is from tip to tip, the chord, how long the wings are from front to back, the thickness of the airfoil over the chord. So this is basically defined by your airfoil shape. The most common numbers are like 0.1 or 0.12, so I just did it from 0.1 to 0.15 and created 5. You could probably reduce this to just one single value in order to make this run faster. Gamma is the sweep angle, so again, you can probably also just replace this with 0 if you want a Hershey bar wing. LF list is the fuselage length, so this is in meters, so from 0.3 to 0.7 meters, and it creates 3 different values for that. The diameter of the fuselage, and the various coefficients of lift that your wings are going to be flying at. I also defined a motor name list and a motor mass list. So I only added these because this is sort of like a placeholder for putting in information about your motors. So this is sort of pre-prepared to iterate through a motor's name, and then you would program it to select from an Excel file that motor's thrust properties and its mass, because the mass is going to affect how much of a payload you can have. So next in this program, it defines a score matrix, and so this is each of the parameters in order and how many you're going to generate. So these 5, 3, 5, 3, 3, 4, 4 corresponds to the number of different values it generates up here, 3, 3, 4, 4. So you may want to change these numbers if you change the numbers up here as to how many it generates. However, if you're just adjusting the range, you don't need to change anything here. So it starts off by iterating through these loops farther down and then overall loops through the bigger loops. And they're just labeled as I, J, K, L, M, and O, P. So again, they are the span, chord, thickness of the wings as a fraction, the sweep angle, length of fuselage, diameter of fuselage, and then the motor name, which is meant to find the thrust basically and mass. However, for here, I just have a single motor, theoretical motor defined. This would also be the type of thing you would iterate through if you were looking through various battery selections, because those affect how long it's able to run for, and then the coefficient of lift. And so it's going to return a total score, the velocity it's going to fly at, and the total mass of the plane. And so it calls the function single plane test, which is shown here. It also, if you'd want to just define single numbers and run this program, it's under plane design v3 central.m, which is not a function. It'll just run and basically do everything that's in here, but it's not available as a function call. So going back to single plane test, you can see its inputs are span, chord, thickness, sweep angle, length, diameter, motor, name, coefficient of lift, and motor. So these two lines here about track distance are basically, relates to the scoring parameters in flying. Essentially, the judges from AIAA define this, and this is how I converted velocity to laps. So it's 2,500 feet, and then I convert that into meters because everything in here is defined in metric. And then I just define motor power and battery energy. Again, this program can be pretty easily configured to convert the motor's name to a motor power, and if you also want to loop through battery energy, for example, you could just switch out the gamma for a battery selections and it'll loop through those. And then you would call to an Excel file and get the properties there, like how many. Yeah, I think this is the total amount of stored energy in the battery. So that's, and I calculated that as the milliamp hours of the battery times its voltage times 3600 over 1000, which converts it from milliamp hour volts to amp seconds. So I calculate the area of the wing as the span times the chord. This is basically a Hershey bar approximation. There you can get slightly more detailed. The equations are going to be in the Roscom thing. The aspect ratio is equal to the span squared over the area. And the constant E is roughly going to be equal to 0.8. Again, I do research on this number to find out what it is. So basically for elliptical wings, E is going to be equal to 1, and for rectangular wings, it's going to be equal to 0.8. And so the more tapered your wings are, the more they go to 1 from 0.8. And then I start off with a velocity estimate, so I'll get a final velocity returned, so you can sort of repeat this process and just keep changing your velocity estimate at the top, so it's better estimates your earlier quantities. So I've also predefined an altitude of flight, a reference altitude, and an ambient temperature in Celsius. So again, these are going to be based off of where you're flying and how high you expect to fly your plane. And so then I calculate the air density. You can probably just approximate this as 1.225, but I decided to use this function here, calculate density. So let me just run this file here. So it'll change back to the right area, and then I can find the file name, calculate density. Okay, so I'm going to pull that up. And so taking in the altitudes and the ambient temperature, it calculates according to equation 1.7 in Roscom. So I'm going to pull that up. Yep, so here you can see it in Roscom, where it defines how the temperature changes, and then I have to convert this from imperial units back into metric units, because again, I'm keeping everything in metric. So this is the to Celsius per meter conversion, this is meters, this is the temperature conversion. Yes, and then this calculates temperature. So I then calculate mu is a constant, that's the kinematic viscosity of air. Actually, that might supposed to be nu, I'm not sure. But yeah, anyway, that's 1.81 times 10 to the negative fifth. Oh no, sorry, it is mu. That's because I'm including rho in the calculation. So then it calculates the Reynolds number in this function here. Yeah, this is a pretty well-known equation in aerodynamics. And then I start calculating the coefficient of drag of the wings. So I calculate the turbulent skin friction drag coefficient. So that's 2.97 in Roscom. Yes, here we are. The skin friction drag coefficient for a flat plate. So this is just approximating our wing as a flat plate, which is roughly true. Again, there are probably more accurate equations, but this one's a fairly decent approximation. So do this on single plane test. Let's see, Reynolds number, turbulent skin friction drag, and then find RLS. What was that equal to? I don't remember. I cannot remember what this quantity is called. X equals cosine of gamma. This is why you always want to label your equations. Well, moving on from that, L prime is defined as 1.2 according to figure 5.15 in Roscom. Yes, here we are. So this is another property of the airfoil. So since I commonly use the NACA 2412, the x of greatest thickness is going to be at 0.4 C, so I used L prime equals 1.2. There are some airfoils where this might not be true, like if yours is if the max thickness is very front forward, then you would change L prime to 2, but I'm able to keep this constant at 1.2. And the S wetted area basically calculates the total area of your wings as you go around the surface. So that uses the thickness and the S of the wing. And then RWF is 1.06 as defined in figure 5.11. So that's the wing fuselage interference factor, which is basically used for calculating non-induced drag. So again, I'm approximating a low Mach number, so you would want to change this. I would preset it though, so 1.06. So I think that's approximating. It is coming onto this line. Yeah, so you may want to repeat this process several times. Once you know your Reynolds number, you want to adjust your wing interference factor, wing to fuselage interference factor. This was what I was getting at the Reynolds numbers I was looking at. And so then it calculates the lift coefficient of drag at 0 lift using this function. So that's equation 5.8 in Roscom. And so a similar process is done with the fuselage. So I find CFF, then the wetted area of the fuselage using the size parameters of the fuselage. And again, these are going to run for each different size based on the iterations. And so it sums up these various contributions from drag into the coefficient of drag for the whole fuselage. So there's the coefficient of drag of the wing due to being a rectangular plan form. Again, if this is not rectangular, you can set this part equal to 0. And then the coefficient of drag of the wing is equal to the combination of the induced section, which I'm going to find. Yeah, so the effective area is A times E. And so this part on the right here is equal to your induced drag, and this is the coefficient of drag at 0 lift added together. So this is the total coefficient of drag for your wings. And then this is for the horizontal stabilizer. So for this one, I basically assumed a constant, assumed it was always, the T over C value was always 0.1, since I commonly use the NACA 0010 for my tail stabilizer. And so the aspect ratio of the horizontal stabilizer is usually half of that of the wings, which is this number here. And I define a constant chord. This you might want to just change as you're working with stability number. Basically, once you get results from here, I would adjust this value to match what you think you need for stability. This is what I commonly use based on the size of the planes I work with. Then the span is calculated from the chord and the aspect ratio. Then I find the area, wetted area. L prime is the same as it was for the previous, for the wing section. No sweep. Find an interference factor, and then I can find the coefficient of drag based on a similar process as to that I used to find the coefficient of drag for the wings. And then this process is basically repeated for the vertical stabilizer. Yeah, so it keeps the same chord at the root and a smaller chord at the tip, and then has half the span of the V-stab. That was something I got from a fellow aerospace engineer. Basically, you want your V-stab to be as tall as half of your horizontal stabilizer. So that's what all these equations mean. I'm defining a constant sweep angle. L prime is 1.2 still. And then I calculate the CD naught for the V-stab. And then my total CD for the entire plane is wings plus fuselage plus the H-stab plus the V-stab. You may want to add on to here any landing gear or pylons, any extra pieces that have not been previously included. You can just add on into this equation, like if I were to add 0.008, you would do it like that. I haven't defined landing gear. It's very hard to calculate. You could use ANSYS to do that and then put it back into this equation. Then drag force over V squared. Yes, these equations here are to find what velocity it expects your plane to fly at. The weight. So this is the calculating the maximum weight your plane can fly at based on your velocity estimate and the given coefficient of lift you want to fly at. And then the mass conversion. This commented out section here is if you were to give it a constant weight, like a total weight for your plane, it then estimates the CL you want. However, I reconfigured the design to give you a coefficient of lift, and then it sets it equal to that. If you don't like that process, what you would do is you would probably run it in plane design v3 central, and then you would basically keep editing the weight test and the estimated coefficient of lift at the top until they match back up with each other. Yeah, here you can see in the looping one, it doesn't include that CL estimate part since it's given here. The mass of the wings, this one is a bit tricky. Estimate wing mass. This was based off of my previous work with it, so it's going to be expected to be proportional to the area of the wings, and then you usually add a constant for like the servos you're going to use. I would probably talk to like a manufacturing team or just go over the design materials and the expected space of the wing in order to estimate this. And then it's similar process for the fuselage and wing mass. You could also enter constants for these based on your expectations. Battery mass here is constant, but this could also reference an Excel file with various batteries if you're trying out different batteries. Adds up the total mass, and then the payload mass is the mass your plane can carry based off your speed and lift coefficient, and of course area as well. And then subtracts the plane mass. Passengers being defined as equal to 10, this is just based off a previous scoring metric from AIAA. So calculate score M1, M2, and M3. Basically take into account your plane's velocity, the distance of the track, the battery energy, and total motor power. So this program here, calculate score M1, basically verifies that your plane can complete 3 laps, and then if it can, it returns M1 is equal to 1, and if not, then 0. Then it returns 0. For this sort of section of the competition. This part is meant to be configured and changed each time for each different competition you might participate in. This is the most malleable part, I'd say. Score M2, this is an example of how payload and the expected time you complete all the laps affects your scoring. So it calculates the time to complete it as the distance of the track times 3 which is 3 laps, divided by the total velocity. And so if the time is greater than 3 minutes, it causes a fail command to be equal to true. And so that'll automatically set the score here to 0. But if not, then it calculates the total energy used and compares that to the battery energy you have. And that also can cause a fail command be true, setting score to equal to 0. So this is basically, if you take too long, you fail, get no points. If you use up all of your battery, which would cause your plane to crash because it has no power, or at the very least glide down, it'll also give you a score of 0. And if none of those happen, however, the score is set to this formula. Again, you would probably place this formula in based on what the judges are evaluating. Calculate score M3 is very similar to M2. It doesn't have any of the previous metrics here, since you could basically infer its success from M2's score. And so this compares the number of passengers you can hold to how long it takes you to complete various laps. And so, yeah, change the equation based on what the scoring metric is. So that's single plane test, and I'm going to run through loop through shape parameters. Oops, sorry that. Okay, just close those and run it. Okay, so I've recently configured the program a bit, mainly changing how this creates the file name for the motor and renaming a few variables about the motor. But it ultimately still works the same. And one set of functions I do want to highlight in particular, since in relation to the propulsion system, is how to find the velocity from the drag and the motor data. So it opens up a motor data file. So these should be titled velocity thrust values underscore, and then you would insert the name of whichever motor you used. And so for every velocity that your plane would fly at, basically the velocity of air passing through the propeller, generates a certain amount of thrust, which is currently in kilograms of force. And so the faster it goes, the less thrust it generates. But of course, moving faster generally generates more points. So there's a certain point where the thrust is going to be equal to the amount of drag you have, and that's going to give you the velocity you can fly at. Yeah, so this is like a maximum amount of force in kilograms. In kilograms of force. So basically, kind of like pounds. So this is like kilograms times 9.81. And so while that's greater than the drag force over v squared, which is imported from loop through shape, or from the single plane testing. Yep, so the drag force over v squared is the net CD times rho times S times 0.5, which is just the equation for drag given CD, but without v squared in it. And so then it calculates the velocity with this file. So to get that Excel file, you need to run motor tests or look up certain parameters for the motor. I'm currently not able to generate them on my own just from theory, but I can work on that eventually. And then this final bit here does linear interpolation between two different force values. I think at the moment it's just approximated as in between the middle of the two, since the gaps between the velocity values are very small, especially as you get higher up. Yep, and so when you run loop through shape parameters, it'll go through all of these different configurations of the plane, It can take a while to run, so I definitely would try to do it on a higher level computer that you aren't in need of immediately. If you want it to run faster, you should lower these numbers here, like 535, 3344. Definitely the length and diameter of the fuselage. There might be reasons why these are fixed at single numbers, so you would change these to 1 and just put in, for these two numbers, the chosen length and diameter. Gamma can also definitely be reduced to just one value of 0, so that makes it run 3 times faster since there's only one loop of it to go through. And we're done. So I think I defined another Matlab file that helps me sort through it. That's not this one. Yes, 8 analysis scores. So when I run this after the loop through ones, it gives me the alphabetical numbers of where this plane performed best because it finds the max of the scores and then returns the I. And so it indexes these, giving me the I, J, K, L, M, and O values that gave me the highest score. Did I forget to? Was there not a P? Oh, I guess I need to update it for P as well. Yeah. There we go. So it works best when I is equal to 5. So that's going to be equal to a span of 3. When J is 1, so that's when the chord is 0.3. So this is very high aspect ratio. When K is equal to 1, so that's a thin wing of a T over C value of 0.1. The length is the first value, which is 0.3. And wants the diameter to be 0.1, which is the M equals 2. Let me just verify that this matches it. Yes, sorry, M is equal to, sorry, let me make a correction there. Yes, I is span, J is chord, K is thickness, L is gamma. So this is with no sweep, and then M equals 2 means that the length is it wants it to be 1/3 of the way between 0.3 and 0.7, so that's about 0.4. It wants the diameter to be 0.05 with N equals 1. O equals 1 is just because I only have one motor choice in there at the moment. And again, the motor will affect the mass of the motor and the relationship between thrust and velocity. And P equals 4 means the CL should be 1. And again, you can change the range of these. And so that is the estimate for my best plane. The way you would affect CL in your design choice would be by changing which of the airfoils you're selecting from and how much of an offset to the angle of attack you want. So an XFLR, that would be accomplished by going to direct foil design. Let's say I'm absolutely set that I want a 2412, although I think it actually said 2410 based on the thicknesses I gave it, would be ideal. So I'm going to save that just as A. And then I go to wing plane design, plane, define a new plane, turn off elevator and fin, because the CL is really just focusing on the plane. Or I'll even input the specific values it wanted, base as best as I can remember them from what I just went over. I'm gonna condense this window so I can put it up side by side with Matlab. Then define plane again. So yeah, based on the values I gave it, it would want a span of 3. So I'll set y equal 1.5, and then it tells it on the sides. 2410 was an example of a recommended airfoil. The span it recommended, the chord it recommended is 0.3. Yeah, the thickness of 0.1, that corresponds to this 10 here. The gamma was 0, so there's no offsets. The length and diameter of the fuselage don't really affect XFLR, and it wanted a coefficient of lift near 1. So let's say you also want your plane's cruise angle to be 0. So only the tilt angle is affecting the coefficient of lift here. So I'll save that and then run an analysis. Say it. I could plug all these I'll plug these values back into single plane test as well. Plane central. So the span was 3, the chord was 0.3, the T over C was 0.1, gamma 0. So I think it wanted a length of around 0.4 and a diameter of 0.05. So if I run this program, I should also clear everything beforehand, just so that it doesn't clog the workspace. The velocity estimate of the velocity it expects to be 28.5 meters per second. So I'll define the analysis at that speed. Make sure you set it to horseshoe or ring vortex and uncheck viscous. And then I'll run the analysis. Actually, I'm just gonna do it at 0, and then delete or reset that. Analyze at 0, since that's what I want to fly at. And I can see my CL is 0.5, so I want to double that, basically. So I'm going to increase the tilt angle until I get to 1, since that's what was recommended by the designer. Yes, and that's about 0.1, so I might want to set the tilt angle of my wings to 9 degrees. I would probably not go much higher than this for a tilt angle. Another option could be that you have a tilt angle of, say, 5 degrees and fly it and the angle of attack you're going to fly at will be 4 degrees, approximately. So that goes over my mechanical engineering based plane predictor. If you have any questions, post them in the comments or go to the Discord and ask questions in the Matlab section.